I'm going to record maybe. Everybody saw me push the record button, right? And it's flashing, correct? All right, I don't know if I did that earlier, but we'll find out. It's okay. So I've got a velocity versus time graph, and if I draw my velocity versus time graph on like this, first thing, what is that going to tell me? Constant velocity. Yay! Constant velocity. So it's a constant velocity. So if I do something and I look at the area under the curve right there, that tells me the displacement. So the area under the curve is going to tell me something. So that's one of the things that we can utilize. So the area under the curve is going to tell me displacement. We will get to looking at this several other times when we're looking at our curves, and we talked about limits. So if I have something that's traveling like this point where I'm looking at the tangent and I'm looking at the slope at that tangent, that's where I'm going to get a limit or an instantaneous velocity. So from a graphical standpoint, that is going to give me my limit or my instantaneous velocity. Okay. Now I can do the same thing with my velocity versus time curve and not be at a constant velocity, actually have an acceleration. So if I have a velocity versus time plot that looks like this, that tells me I have a constant acceleration. Now one of the caveats, and we don't harp on it enough because we end up using it and we end up dealing with it and we end up looking at this problem, these problems, we are dealing with a situation that we are utilizing a constant acceleration. And for the purposes of general physics, or physics 1 and physics 2, where we are now, we are not going to mess with a changing acceleration. And we can actually deal with that on a routine basis fairly well. And we can get a lot of information, and we don't have to enter the world where we're going to get a changing acceleration, because that's not where we're going to play. We're going to play with a constant acceleration. So this is a constant acceleration. And if I do this, I still have the area under the curve as my displacement. Okay, I still have the area under the curve as my displacement, and I can just add up those areas. So we can start to look at it from that perspective. Now, when you guys get into calculus, and the whole idea behind calculus is I'm going to do these incremental little things. I'm going to do these incremental pieces. If I am going to integrate, what I am doing is I am taking these little rectangles along the way, and I'm adding them up smaller and smaller and smaller, and I can actually do this on Excel and get the value that's going to be similar to an integral. So the area under the curve is just a big sum of a whole lot of little slivers. And I can do it on incrementally smaller and smaller and smaller things, and I can actually do what we call the graphical method of doing an integration, and I can do that, and I can do an integral. So that's where the integral is going to come from. So that's where, so essentially what happens is sum ultimately comes into that, because this is going to be kind of, these would be like I'm adding up 3 particles. These are like I'm going to add up so many more particles, and I'm just on an infinitely smaller basis. Now, one of the examples in your book says, I have a position versus time equation that looks like this. I'm going to start out at an initial position, then I'm going to travel at some acceleration b times t squared, Then I'm going to do something like a c times t cubed, and that will describe the motion. Okay? That will describe the motion. Now, because most of you haven't even gotten there in calculus yet, to introduce it like in week 2 of physics, you're going, okay, this looks like hokum. But what we're going to do is we're going to do this incremental step, and this is going to make life look a lot better, because remember we said velocity was a change in time, or a change in position versus a change in time. We said we could do it that way. Well, guess what? I could get my Excel out and I could crunch through this, every incremental little itty bitty piece, but calculus says that this is a derivative. And that makes life easy, because what you guys are going to learn is if I do a dt of some function, and that function is an n, what that's going to give me is n times the function n minus 1. And if n happens to be 1 and I take off 1, I get f to the 0, and we all know what that is. That's just the number 1. Okay, so f to the 0 power is just 1. So this is my general form for my derivative, which I can look up on derivative tables. Yay, derivative tables. Which the calc teachers, they're going, uh-oh, she's already teaching shortcuts. Yeah, she's already teaching shortcuts. So, but what that says, if I'm going to use this function here, and I take the derivative of x with respect to t, this is going to be, there's no function x here, that just goes away. There's no f associated with it. So we're doing this with t. So this is going to be b times 2 times t. And this is going to be minus c times 3 times t squared. And we now know that that's a velocity. Well, now we also know from last week that velocity is a change in, or acceleration is a change in velocity with respect to a change in time, which means I can take that derivative of my velocity equation, which we now just calculated as 2bt minus 3ct squared. This now becomes 2b minus 6ct, and that's my new description for acceleration. So we can do a variety of different things to help us out. And that's just the math for it. Okay? That's just the math for it. And for the purposes of this class, because you guys haven't had it in calculus yet, I show it to you. Because somewhere down the way, somebody's going to say, well, you had this in General Physics 1. And you're going to go, okay, that was a long time ago in a land far, far away. I'm going to look at my book again. And our author does a really good job of presenting it really clearly right now. It's probably one of the best that we've got. But that's where all of that is coming from. Okay, that's where all that's coming from. So we're going to play a couple games. Okay, we're going to play a couple games. So first thing what we've got is anytime you've got a problem, all right, anytime you're given a problem, step 1 is read the problem. Step 2 is figuring out what they asked for. Okay, step 2 is figuring out what they asked for. So we're going to use a Nimitz class aircraft carrier. I actually happened to look up today some information about a Nimitz class aircraft carrier. Now, a Nimitz class aircraft carrier is like a postage stamp on the ocean. Actually, even if you've seen a Nimitz class aircraft carrier, which is a big, huge floating island, and then you realize somebody's got to land a plane on that, you start thinking about that a little differently. Well, the runway on a Nimitz class aircraft carrier is, if I remembered it, I forgot to bring my little piece of paper, but I just looked at it. 333 meters. Think about that for a second. That's essentially 3 football fields. All right. Has everybody flown on a plane? Everybody flown on a plane? Everybody, whether it's a regional jet or a big 737, any one of those. All right. Average takeoff speed for a jet is somewhere between 155 miles per hour to 170 miles per hour. Average takeoff speed. Okay. To take off, use a 737. I looked that one up today too. The average takeoff time for a 737 to go from 0 to 170 miles an hour to take off is between 30 and 35 seconds. Okay? So for 737, we're doing 30 to 35 seconds to take off. And when we take off, we're taking off at 170 miles per hour. So let's calculate if that jet is taking off at a constant acceleration. Let's calculate the acceleration that the jet takes to accomplish that task. So we're going to calculate acceleration. So what do I know?
The distance, you know.
Do I know distance?
The distance it has to travel.
I'm talking 737, not Nimitz class aircraft carrier. I'm going to come back to that.
You know it's speed and time.
I know speed. Well, I know.
Your initial velocity and your final velocity.
I know my final velocity and I know my
Initial.
initial velocity. So I know my initial velocity is 0. My final velocity is 170 miles per hour, which is going to be a pain in the butt because I'm in seconds, right? And we're in physics class. It's going to be a pain in the butt because I probably want to be in meters. So let's, because I'm going to end up comparing to meters, so I kind of want to be in meters. So I got to convert that 170 miles per hour to meters per second. So now here comes the fun part. The one thing I dislike about Kat's, her book, is she doesn't have a handy dandy table like this easily accessible in the cover. Okay? There are some conversion factors that you gotta find those, so we gotta come up with our conversion factors. We're gonna do that. So I'm gonna use that 1 kilometer is 0.6125 miles. All right, so we're going to put this in kilometers, and this is 0.6215 miles. And is everybody comfortable with me going ahead and saying that 1 hour is 3,600 seconds? Okay, we got 1 hour is 3,600 seconds.
Do I have to go from meters or kilometers to meters?
Yeah, but right now if I just do this, then it's just move the decimal point. Yeah, so I get 170 divided by 0.6125 divided by another 3,600 gives me 0.07598. And if I multiply that by 1,000, because there's 1,000 meters into a kilometer, that's 7598 meters per second. And for just to keep numbers simple, we're going to go to 76 meters per second. So that's going to be 76 meters per second. So I have time, variables I have are time, and I have the velocity, and I want to know acceleration. So let's look at my kinematic equations that I have readily accessible. Alright? I have that position is equal to velocity times time when acceleration is equal to 0. So if I'm traveling at a constant velocity, I have position is equal to, and this is change in position, is equal to my initial velocity times time plus 1/2 AT squared. That's one of them I've got. Then I have velocity final is equal to velocity initial plus the acceleration times time. And then I have that velocity final squared is equal to velocity initial squared plus 2 acceleration times my change in position. This is likely the one that I'm going to use because I want to find acceleration. So I got to rearrange it. So acceleration is going to equal the final velocity minus the initial velocity divided by the time. My initial velocity was 0. So now I'm at 76 meters per second. And we're going to go ahead and use 30 seconds. So my acceleration is going to be that. My acceleration is 2.53 meters per second squared. So now I want to know, because we're going to come back to the limits here in a second. Limits class. We're going to come back to that in a second. So now I want to know the distance my runway has to be. Okay? In order to let the 737 take off. So if I now have acceleration, I have the velocities, and I have time, but I want to know distance. I can do a couple of things. I can do this, because I have time, I can use that one, but I'm going to use this one because it's easier, there's less variables. So I'm going to have velocity final squared minus velocity initial squared divided by 2 times the acceleration is going to equal my change in distance. Everybody okay with how quickly I did that rearrangement, or do I need to do it step by step? You guys good over there in Enid? Okay. All right. So let's plug in this 0, right? So now I've got 76 meters per second, that's squared, divided by 2 times 2.53 meters per second squared. Now let's just make sure I did everything right. Let's look at the unit analysis. I got meters squared divided by second squared divided by meters second squared. Second squareds cancel. One of my meters go away, and I'm actually in meters, so life is good on my unit analysis. Now if I do 76 squared divided by 2 times 2.53, it says I've got to have 1,142 meters for that jet to take off. We got a problem. If I do my calculation right, that's like 3 times what I got on a Nimitz aircraft carrier. By the way, the distance of your runway, not whether or not you actually have international flights, is actually what distinguishes a regional versus a national versus an international airport. Okay? But the distance of your runway actually what classifies what kind of airport that you have. Because it dictates what kind of aircraft can actually land there. And has more to do with landing than it does taking off. Because we can do this same calculation for a deceleration as well. We can do that same calculation for a deceleration, but that's what actually distinguishes what you can actually have land or take off at a particular airport. The Amarillo Airport is actually an international airport, and it has, and I've seen it, it will handle the great big Soviet cargo plane. That thing is a Hummer. That one, if you look at it and you go, I don't know how it gets off the ground. Anybody's ever seen a C-130, it makes a C-130 look puny.
I mean, to be fair, C-130s aren't that big on the inside.
Well, but it's still, this thing, and I think the biggest US one is a Hercules. Hercules?
Galaxy.
Yeah,
It's the Galaxy.
Yeah.
It's the biggest.
the Galaxy, but that Soviet one makes that one look puny. It's a big aircraft.
What is it called?
The Antonov.
Yeah, something like that.
The big one?
The big, the Soviet aircraft. That's the largest cargo aircraft that's around.
I thought Airbus had a beat by now.
Well, from a commercial standpoint, that's still the one you go to. And actually, its dimensions are such that it's still to transport things like compressors. It's still the one you gotta use. It's a big boy. It's a big boy.
It's a lot of wheels on it.
Oh no, it's a big boy. It's a big freaking aircraft. They actually did. They brought them in. They landed one at Amarillo because they were bringing in and out, taking some equipment out, oil field equipment. Yeah, it's a massive sling. But like I said, you're talking that right there. That's the runway on a Nimitz class aircraft carrier. That's what we gotta have for some of it. Now, so let's take other details. So how does the plane take off on an aircraft carrier? It's not that it's gonna use that runway to take off. It uses a catapult system, right? Everybody knows it uses a catapult system. It goes from 0 to 170,
Real quick.
2 seconds. So let's calculate the acceleration, because we can do it, right? Let's calculate the acceleration. We already did 170. We know that 170 is 76 meters per second. And so now we want to calculate the acceleration. We got velocity final is equal to velocity initial plus the acceleration times time. So we know velocity final divided by my time is going to be my acceleration, because we know that that is 0. And so we get 76 divided by 2. We get 38 meters per second squared. So now you want to calculate, we talk about G forces, right? We talk about G forces, we talk about G's. How many G's is that? Well, we know that gravity is 9.81 meters per second squared. So if I take my 38 meters per second squared, divide that by 9.81 meters per second squared, it's 3.9 G's. It's essentially 4 G's. Kyler, you got your computer out. Look up the top speed of a funny car dragster.
Okay, what dragster?
Funny car dragster. Just,
Funny car?
yeah, funny car.
Top fuel's better. More fun.
150. This says capable of speeds in excess of 330 miles an hour.
330? Okay. All right. So if we do a 330 miles an hour, and they do that in a quarter mile, right? Because we're at the track, they do it in a quarter mile. So if I do my 330, because we've already done that lovely conversion, right? So I do my 330. I'm getting that that's 140 meters per second. And 1/4 mile is about 403 meters, if I did that conversion correctly. So we can do the same calculation, 147. I gotta go back and calculate that, hang on. We gotta go back and calculate distance. So we do 147 squared divided by, oh, I mean my acceleration first. So we get V final squared minus V initial squared divided by 2 change in X will give me acceleration. This is going to be my 147 squared divided by 2 times my 403. I think 403 was a good engine in cubic centimeters. 147 squared divided by 806. Gives me 26.8 meters per second squared. Divided by 9.81 gives me 2.7 G's. Just for comparison purposes. Just for comparison purposes. So you can do all kinds of fun things. Pick up Car and Driver. You can pick up all these different calculations, be able to do them without too much fun stuff. But the key becomes, what is the question being asked? And when is the question being asked? So let's look at, we're up here on a cliff. Okay, we're up here on a cliff. And we drop a pebble or stone down. And it's going to hit the bottom. Now if I'm dropping it, it's going to have an initial velocity of 0. And we're going to make the assumption that we don't hit what's known as terminal velocity. Okay, we're going to make the assumption that we don't hit terminal velocity. Because what terminal velocity is if I have an object and I end up coming down, there's enough drag in the medium, i.e. the air or the water or something like that, that will not allow me to go any faster. It just won't allow me to go any faster. We get enough drag, we get a terminal velocity, and the terminal velocity it's based on a number of things, but we're going to make the assumption that we're not going to hit terminal velocity. And we're going to have a person down here, and we're going to have a person up here, and we all know, you all are going to find out that my artiste ability is limited. And this person with the stopwatch is going to say that it takes 3.0 seconds to complete the fall. Now, because we're in the y direction, we do have a constant acceleration, gravity. So we have a constant acceleration of gravity, which is 9.81 meters per second squared. So at this point, I can ask you a variety of questions. One question is, what's the velocity at the bottom of the fall? Well, that's easy. I get my velocity final is equal to my velocity initial plus AT, and now we know the initial velocity was 0, and now I put my,
Down the papers.
no, and now I've got 9.81 meters per second squared, and I've got 3 seconds, and now this is gonna be 9.81 times 3. This is gonna be 29.43 meters per second. Now, here comes another fun part. What if I get one of our pitchers and they throw the ball down instead of just drop the ball? And we'll say they throw the ball down with, we're going to say it's a slow. So we're going to use 27 meters per second as the throw down. Well, if that's the case, I got to put my 27 meters per second, and then I have to add that 9.81 meters per second squared times my 3 seconds. And now it's going to be plus 27. It's going to be at 56.4 meters per second. Now, a couple of things. When we deal with a situation like this, we may be able to break the problem up, okay? We may be able to break the problem up. One of the things is we know what's happening, so we're gonna actually, I'll do a problem here with we're gonna use a plunger like on a pinball machine. And I pull this back and it's gonna hit the little ball, and the ball is gonna proceed off at that point. If there's an acceleration at this point from here to here, once the ball leaves the plunger, there's no more acceleration if I am going in the X direction. I'm not going to have any more acceleration in the X direction. There's nothing that's going to cause more acceleration. So when we look at these problems, we may have to break them apart. We also may have to look at what they're asking. So let's look at this problem a little bit differently. How am I doing on time? Oh, we're about to be gone. I didn't even get as far as I wanted to today. Oh well.
We'll push the homework back, Joan. Push the homework back.
No, because you got everything you need. And I'm in my office tomorrow. I'm in my office tomorrow.